Okay, so 15b, universal derivation. So what's universal derivation? It's like conditional derivation. It's a way to box and cancel show lines where what we're trying to show is a universal generalization. So why would we want that? Well, the quantifier negation rules are derived rules. And so if, for example, we wanted, and let's say we were trying to derive one. So suppose we were trying to derive this one, not sum x fx if and only if for all x not fx. And so we'd have this first conditional, so it's not the case that sum x fx, then for all x not fx. So we'd say assume cd because we're trying to show a conditional, and then we'd say show the consequent, and we might say assume id, but if we don't have the qn rules enabled, we can't do anything with line 5, and so it doesn't help us. We could do show on neg of 5, but that's just repeating the show line of line 4. So we need a way to show universals. Or, well, we need a way to get universals, and the way in which we get universals is we have a method of boxing and canceling. So let's see how that works. I'm first going to give an example of universal derivation in English, and that will make it clear why it's sort of what it does and why it makes sense, and then we'll look at how it works in the system. So let's consider this argument. Every penguin can read. Everything that can read has read Proust, therefore every penguin has read Proust. Well, it's not a sound argument. The premises are false, but it's valid. Any interpretation of the logical vocabulary on which the premises are true also makes the conclusion true. So how might we establish this? Well, suppose something is a penguin. According to the first premise, it can read. And so given the second premise, it has read Proust, and so every penguin has read Proust. Okay, so let's look at this argument. We have this something and the it and the it. So those are like effectively that something is operating a little bit funnily. It's actually operating like a free variable, and the two its are also operating like free variables. So what we do here is we assume an arbitrary, we argue what we try to do is show that an arbitrary penguin, we don't know anything about it except it's a penguin, given the premises, it has read Proust. So we show, what we do is we get an instance of the claim. So there's the general claim, every penguin has read Proust, and we establish an instance of the claim, some particular penguin has read Proust, except that it's actually effectively, we're establishing it for an arbitrary penguin. So there's no particular penguin we had in mind. It wasn't Opus, for example, and it wasn't any of the penguins at this zoo that we've seen read Proust. It's an arbitrary penguin, and because it's arbitrary, the derivation actually works for all penguins, and so we can conclude that all penguins can read. So we show that an arbitrary object has the property, but this works only because we start with no information about the object. If we had some information about the object we were reasoning about, it wouldn't be arbitrary, and so the reasoning wouldn't work for all objects. Now, in the case above, we did make an assumption. We said, suppose something is a penguin. But we did that because that's a conditional assumption, right? If what we want to show is that given that something is a penguin, it can read Proust. And so we assume something is a penguin. But we're assuming that some arbitrary object is a penguin, and we're showing, given that assumption, it follows that it can read. So it's okay for us to make assumptions about our arbitrary object, given that we're clear that that's what we're doing and reasoning effectively. So that's fine. We don't actually, yeah, okay. So let's consider what universal derivation looks like in the system. So we start with show for all x fx, and we proceed, and at some point we get fx. So this is the sort of the arbitrary object that has the property, and we say we cite the line on which it occurs for universal derivation. So if we have for all x fx we have show for all x fx as a show line, then we get the instance, and we're good to go. Now, the instance has to match with the variable. So if it was for all y fy, then we'd have to get fy. So it has to be, what we get is just remove the universal quantifier from what we're trying to show and get exactly that. But there's a restriction. Oh, sorry. There's no particular assumption we make. I'll talk about some strategic issues in a slide or two, but there's no assumption you make. The indirect assumption would be not for all x fx, and you apply qn, but if you don't have qn, that's not relevant. There's also a restriction, which is this, that the free variable in line 5 that it's the variable we're quantifying on, so the variable that shows up in the universal quantifier in the show line, that cannot be free above the show line on earlier available lines. Why do we have that restriction? Because we have to show that x has f for arbitrary x. But if we have a whole bunch of information concerning x, then we won't have shown that an arbitrary object has x. We'll have shown that that object that we have that information about has f. So then the way in which we incorporate that restriction into our system is x does not appear free above the show line. Okay, so what would a universal derivation look like if it was complex? Well, you can do universal derivations for complex formulas. So if it's for all x, if fx then gx, then take off the universal, what are you left with? If fx then gx. So to do universal derivation here, you have to get if fx then gx, just like we see here. Now, there's an associated show strategy with universal derivation. So if you say, if your initial thing is show for all x if fx then gx, then you could show that you could do immediately another show line, so show the instant, so you'd say show if fx then gx. And once you complete that, who knows how you complete that subderivation, but once you complete it, then you'd say, again, universal derivation. Why would you do this? Well, line 3, because you can then make an assumption off of your second show line. In this case, you could say line 3 could be fx assume cd, or who knows what it is. But the point is, when you do show instance, you can, on the one hand, when you finish box and cancel the instance, then you can immediately do a universal derivation of the initial show line. But also, this second show line lets you make an assumption, and that will help your reasoning proceed. So that's, if we go back to the derivation we were looking at, so we want to show for all x if fx. How would we do that? Well, we could say show instance, not fx. So if we can get not fx, then we're done. Then we can box and cancel line 4, because that's a universal derivation. And we can make an assumption here. So we could say assume ID. That's really the only thing we could do. Now, what should we do next? I'll leave that to you to figure out. But this is the beginning of this derivation, so you'll find this helpful. So yeah, you want to use this show instance, and once you're done here, however you finish it, then you can say 5ud for universal derivation, and then you can say 4cd, and that direction of the derivation is done. And you're going to want to do derivations of theorem 204 and also 203, which is the other main version of QN. There's also 5, 6, 7, 8, and 205 and 206. Well, you can see their examples are done, but those are useful versions. But the most important versions of QN are 203 and 204, so you're really going to want to derive those. So that's it for, well, maybe I'll do an example derivation or two, but that's it for new derivation content. The rest of this week, this unit will be concerned with introducing models.